All right. So we're just going to continue where we left off last time, and essentially the topic that we're still trying to figure out is the wave particle dualities. And previously, before we finish up in our class with this particular concept, we went into just kind of calculating wave length, frequency, and energy of quantum mechanical objects, and specifically we make a distinction, that is, if you have a photon, which is just particles of light, versus everything else, the equations is slightly different to determine the wavelengths of that thing, of that particular object. And essentially, if you have one of the information, you should then be able to use it to figure out the frequency as well as the energy. Majority of the time, I like to use it on the wavelengths just because it's a little bit easier to understand than the frequency. But in any case, so we begin our class with this, and then we end up our class with wave particle duality, and specifically we went into the double slit experiment. Hello. Chemistry? Yes. Welcome in. No, it's still me. Yeah, it's still me, but I'm going to print out something later. Would you mind working with Paul, I think? And would you mind just like sharing the class planner a bit? I'll print it for you as well in just a bit. Since you're just here, some of the materials that we have done in class, I uploaded to Canvas already, but sometimes there's interactions, and sometimes I switch it around to YouTube videos. That's why the videos are truncated into little chunks. Yeah. I would say Amazon is the best way to go. And if you don't want to get the newest version, you can just use any of the older versions, and it should be okay. Yeah, but it's a good addition. But what I try to do is I print out essentially everything that we needed into that smaller packet. So hopefully it still. Yeah. So those are already up on Canvas as well. Did you? Sorry, I didn't catch your name. Anthony. So did you email me last week? Yes. Thanks for rescheduling for today. So at some point we're going to do some exercises, and I'll catch you up in greater detail. But most of the time, the materials that we've already covered is already up online. Yeah. So I'm just kind of recapping what we did last week. We did some calculation in terms of calculating the wavelength, frequency, and energy of quantum mechanical objects. And essentially, if you have a photon, which is a particle of light, the equation is different with pretty much every other object, like protons, electrons, or pretty much everything else. Because photons is a bit weird. They move really, really fast, and they have no mass. So they're just a weird-looking particle. And then we went into wave particle duality, and specifically talk about double slit experiment. And just the conclusion from this particular experiment is that a photon, or at least in the 1800th edition, experiment edition, is that a photon is a wave. And of course, there's always, the things about science is that everything gets updated. So you have the 1920s. Once you have better instrument, you have then photons. When you try to fire one particles of light or one photon at a time, it looks like a particle. And of course, once we get into much better interpretations, what we figure out is that it's both particle and a wave. So So that's the small conclusion that we get from there. But we're kind of moving through, not linearly through time, that's why we're kind of jumping around. But in total, there's actually 3 experiments that's actually really important. The double slit experiment is one that's more comprehensive and is easiest to understand because we're not going to do any math on it. And if you remember, the observation is pretty straightforward. That is, if you have one particle of light that you pass through just a little tiny hole, and what you find is that on the other side of the wall, instead of having just 2 bright spots, what you'll find is actually a distributions of fringes of light and dark, and I'm just trying to show that the one that's with the highest thing here is the bright spot, and what you have there is a dark spot. And that solely happened because in this case the light is actually behaving more like a wave rather than it's behaving just a normal particle, which you will not see if you try to do this with, say, baseball or something. You will not be able to see this type of distributions. What I do want to move along with our thing is the photoelectric effect. Oh, actually, let me backtrack. Let's put the photoelectric effect on the bottom and the black body radiation on the second one, just because it's a little bit more in terms of where the experiment began and so on. It's a little bit more chronologically correct. And we're just going to discuss really quickly the contributions of the black body radiations, and we'll do some math on the photoelectric effect, and then at that point I'll catch you up in a bit. So far, we've been using this symbol H, which is what we call as the Planck's constant. And this particular constant value have a value of 6.626 times 10 to the negative 34 joule second. No, well, you need to know what H is, and you should be able to know that. I'll give you a list of what they are, but you should be able to, it's like, this is H, I need to use out of a list of, you'll see like H is equals to something, C is equals to something else, but you need to know what they are. And essentially, if you look at your textbook, even you'll probably see, or even if you want to look at it on Google, you'll see that Planck has essentially contributed to the father quantum mechanics. Although his contributions is a bit it's not the most direct contribution ever, and essentially what he has is he was actually not thinking about quantum mechanics, and he wasn't thinking about science in particular. He was actually commissioned to try to fix a light bulb, to try to make a light bulb better, because what they found is that he's essentially just kind of hired by a light bulb company to make their light bulb more efficient. And essentially what happens before, I'm not going to go into the mathematics, so you don't need to know this equation here, don't worry too much about it, is that based on an older theory, which is what they call the classical theory, when an object, or I should say any object, contains some energy associated with it. And essentially, because the wavelength that we have is, each wavelength have some frequency and some wavelength as well. And essentially, the previous theory that calls for some of the solutions says that if you have an object or a photon with large wavelength, you can't fit that much because the wavelength is big, whereas your object is finite in size. Whereas if you have an object with really, really small frequency, really small wavelengths, you can actually fit quite a bit of them because the wavelength is small, so you can fit tiny objects better in a small. You can fit these smaller wavelengths better in objects, and you can shove more into it. And of course, what we learned from last time is that if your wavelength is small, your energy is going to be high. So essentially, the theory, at least in these 1900s, is insufficient to actually describe what people see. That is, if you have your light bulb, so this is the old incandescent light bulb, and you heat it up to 3000 Kelvin, then the spectrum that you will see looks something like this. Whereas if you heat it up a bit more to 4000 Kelvin, it would look closer to the other one, and so on. Essentially, initially, it follows pretty well. It goes up. The theory is never perfect. It goes up, so it's close to the classical theory. But what happens is that at some point, it plateaus off. It gets really high, and it just drops back down. Whereas in the old classical physics theory, it's just you can fit more, the higher the energy of the wavelength, the more you can fit it into the object. So what you'll find is that you should see more and more, an object would then have more and more of these high energy waves. And that's not, and obviously that's not true, because if that were true, any object, because the smaller the wavelength it is, the more they can fit into it. That means any object, regardless of whatever temperature it is going to start emitting gamma rays and X-rays and really high energy radiations just because you can fit more into it. And obviously I'm not emitting gamma rays, so none of you guys are dead. Otherwise everybody would be dead immediately after you were born, just because everything is emitting gamma rays. So clearly the classical theory is incorrect, and essentially he's trying to figure out why it is incorrect. And since we are looking back in times, the answer was not particularly clear. So he came up with kind of a wishy-washy argument that, okay, maybe it is the case that these wavelength with the shorter wavelength photons, so light with shorter photons length, like a gamma rays or an X-ray, is actually higher in energy. So he's basically just saying, like, okay, these things are higher in energy, whereas things with longer wavelength is going to be lower in energy. And essentially what he's saying is that, well, if I have an object like my phones or your chair or table or even the sun, they don't have an infinite, all object doesn't have an infinite number amount of energy. So what happens is if you try to put smaller and smaller energy wavelength into it, there's not enough energy in the universe to fill it with that amount of energy. So essentially what he has is that he says, like, okay, they're just going to distribute themselves equally in terms of probabilistically. That is, you can't have too much of the higher energy, whereas, but you know that actually I'm not explaining this as best as I should, but essentially you can't have an infinite number of this higher energy wavelength inside a particular object. Therefore, at some point, as the energy goes up, initially it's okay, but as the energy goes way, way up, there's simply not enough energy and it's going to plateau down. So that was his wishy-washy argument, that these wavelengths have higher energy, and specifically, and why his name is important, that the energy of these wavelengths, of the photon, is proportional to, equals to h, which is the Planck's constant. So he made this up times the speed of light divided by the wavelength of the photon itself. So essentially he's just like, okay, I'm going to do these calculations, and based on my observation, I figure out that h, I calculated this to be 6.626 times 10 to the negative 34 joule second, in terms of its proper units and so on. So it was actually just kind of more of a thought experiment. He said, it was like, okay, I don't know why that the energy of the smaller energy, this shorter wavelength is higher, but it is higher. And based on my equation, which is what he wrote over here, we're not going to go into it. The result pretty much fits exactly with the observation that you would see. That is, if this is what you will see, what you will observe, if you were to try to calculate this particular equations and plug in all the values and so on with that temperature, you get pretty much exactly on the line. So he knows for sure that his equation is right, and somehow, in the grand scheme of things, that higher photons with shorter wavelength is somehow higher in energy, but he doesn't actually explain it very, very well. Somehow, everything fits into the equations on the bottom here, and just that, and which indicates in that regard, the energy of a particular photon is inversely related to its wavelength. What I do want you to know, at least for what I keep seeing in terms of like testing and so on, because sometimes I do have to teach to the test a bit, what I expect you to know for these black body radiation is simply how to draw the graph and how it looked like. That is, the conclusion is pretty straightforward. That is, if you have a hot object, so this is wavelength, so wavelength. If I were to have a hot object, so I'm going to use a red color. Hot object contains more energy because it's hotter, so it's going to emit more shorter wavelength photon. So if you have a hot object, you'll see the distribution to look like that. So this is hot, and this is the y-axis is probability or intensity. That is, if you have a hot object, then it's going to radiate higher energy photons. So if you think of the sun, it's about 10,000 Kelvin, and it emits the entire spectrum of light that you see. Whereas if you have things that are a bit colder, say, maybe I should use the color orange. So if you have things that are medium in heat, so say medium, well, if you have a medium temperature object, what you'll see is that initially it's going to go up, but it's not going to, for one, the intensity is lower, so cold object doesn't emit as strong as a radiation, and also the maximum of the wavelength emitted is going to be larger, or sorry, longer wavelength, which simply means lower energy. And as you go colder and colder, what you'll find is that it's going to look more like that. So the blue one here is cold. So that's kind of the limit that I want you to be able to know. That is, hot object will emit higher energy photon. Essentially, just kind of the reproductions of the graph that we have printed already in here. Right? Just reproductions of that. So the sun, for example, if I continue with this particular explanation, you'll see that the sun still emits some UV ray, and it's essentially just every color in this, the visible light that we can see. Whereas if you have a somewhat smothering coal, what you'll see, because we only able to see a slice of the entire radioactive radio spectrum, what we can see is like an orange or red color, because the red color is a little bit lower in energy. But the idea is pretty straightforward. That's all I want you to do, and be able to distinguish. So now it's pretty much the contributions of Planck's, which is Planck's black-body radiation. So black-body radiation somehow from the equation tells you that the energy of a photon is inversely related to its wavelength, but he's not exactly sure why. It just fits exactly with experimental data, and sometimes when your experimental data fits exactly with your theory over and over and over again, there must be truth into it, although you may not exactly know why or the explanation is not exactly clear. Intensity. Right, so hot objects have more intensity. Right. I'm going to skip this whole thing because we don't really care about that too much. And go into and jump around into the photoelectric effect. We'll do some math here and then I'll print out your stuff. Mike? No, it starts with an A. Anthony, thank you. So I'll print out your stuff in a bit as well, so it should be easier to see. So that was, the blackbody radiation was around 1900, and of course we came into the photoelectric effect, which is the last one of our 3 important experiments. And a lot of people don't know this, but Einstein actually had his Nobel Prize based on his explanation of the photoelectric effect. It's actually the same explanation that Planck's get, but it's just much better and much easier to understand experiments as well as explanations that the energy of a wavelength of a light is proportional to its wavelength and frequency and so on. Now, in terms of the photoelectric effect, I'm just going to summarize it. The contribution is 2 things, which is the energy of a photon is related to its wavelength again and frequency, so that's one. But the second one is that photon also behave like a particle. Okay, so those are the 2 things. That one is this equation becomes much easier to understand and experimentally easy to see, and the second one is we're going back that photon behaves like a behave like a particle again. So let me explain the experiment a little bit in terms of the photoelectric effect, and then we'll do some calculations and things like that. Okay, so the experiment is pretty straightforward. You have a piece of metal, so say aluminum or silver or gold or whatever it is, and the experiment is pretty straightforward. In the old days, what we measure of energy has nothing to do with the wavelength of the photon, because we didn't know anything about the relationship between the color of light versus its actual energy carried per individual light particle. What we know is that you have an electricity socket, and what you measure as the amount of energy is essentially just the amount of energy that is being delivered by electricity or electrical current. And what you know is that if you have an intense beam of light, it's going to carry a lot of energy here, high energy. So the more intense a light is, then it has more energy because you have, more intense light. So that's all people know before, is that the energy is somehow just only related to intensity. But what happens is that in this particular photoelectric effect experiment is that if you have a red light and you shine it into this particular, in actually any piece of metal, if you shine red light into it, I'm going to try to show this in large wavelengths, and what you see is that nothing happened. The light bounces off the surface of the metal, but nothing happened at all. And if you do the same experiment now, but with high intensity light, so instead of just kind of little trickles of just one photon at a time, you put in a huge amount of photons all at the same time. So you're delivering a huge amount of energy, but what you'll see is that there's nothing happens either. Okay? You see that the light bounces off the metal, but nothing happens in general. But what happens is that if one were to repeat this experiment with UV light or any shorter wavelength photon, so I'm trying to show this as a shorter wavelength, you can just kind of do a very low intensity, and what you'll find is that electrons start being ejected out, electrons being spewed out from the surface of the metal. So these are electrons. Okay, so again, all we know about energy is that the intensity of the light is somehow proportional to its energy, but I can use a really, really high intensity light, red light, nothing happened, but if I were to use a low intensity wavelength of light, with UV in this case, I see electrons being ejected out. And of course, if I use an even more intense beam of UV light, I see a lot more electrons being ejected out. So these are the observations that you'll see, or what a lot of people have seen before Einstein, in terms of the photoelectric effect. So why is it the case? And how did Einstein figure out how to solve this particular problems? And his solution is actually pretty straightforward and quite simple, which is why it's in the textbook, because it's rather an elegant one. And essentially he's just saying that energy is conserved. In order for make something to happen, then you have essentially the electrons is now being ejected out, but you have to pay some amount of energy for that to happen. And essentially what he's saying is that the energy of the photon that you fire into the onto the surface of the metal is going to be equal to the energy, or I should say the energy of the electrons ejected out, so let me put it on here a little bit, the energy of the electrons ejected plus a work function which is basically the energy that you have to pay in order for this particular process to happen. So the best way to think about it is that you're trying to pluck like a cell phone off the surface of this particular podium. You have to have there's some energy cost in order to do business, essentially. And hence this is where the mathematics goes in. Since we're talking about the photon, and essentially Einstein just took Planck's equation and just said the energy of the photon has nothing to do with the intensity of the photon itself, but rather it's related to the energy of the individual light particle. So light now becomes a particle, and that light that you shoot into it is just one light at a time, and each particle of light have an energy of hc over lambda. So this is the energy of your photon, is going to be equals to the energy of the ejected electrons. And because we know electron have a mass, and this is physics is pretty well understood, the energy of any moving object is just equals to 1/2 times the mass, and I'm going to put an E here in the bottom to say that this is mass of electron times the velocity squared. So this is the velocity of the electrons. Electron plus the work function, which is essentially the amount of energy needed to remove electron from the surface of the metal. It's basically the energy cost. This is the symbol is that one, that's the work function. And essentially every metal have a different work function. So lithium has a work function of closer to 2 electron volt. Gold have a work function of 3 electron volts, and so on and so forth. So essentially every metal is slightly different. So that's kind of the equation that he got, or he proposed. And for one thing, it validates this particular equation, which is in quantum mechanics is a huge one, because somehow the photon and the wavelength is now interrelated, and in this particular matter you can see pretty well that the relationship is pretty exact. That is, so I'm going to continue with this particular equation. So if I were to go back to our example here again, if I were to shine red light with long wavelength, so this is red, I see nothing happen, right? If this is red or long wavelength, and only until I go into some energy of the wavelength that's a little bit above the threshold, which is in this case the work function. So I'm going to try to draw this with the shorter wavelength. If it's just enough, if the wavelength is short enough, what you'll see is that the electron is going to get shooted out from the surface of the metal. So this is metal. Metal with some work function something. Right. And the experiment, the beauty part about this experiment is that the equation says that if I were to shoot instead of an even shorter wavelength photon, the equation tells you that the electrons is going to be ejected, but now it's going to move even faster than the previous one. Right? So high energy photon. It's energy of, if you have an object moving, the faster it moves, the higher its energy. Yeah. Yeah. So essentially, not quite. Let's do it this way. So you have, let's think of the electrons as a box. And let's say if you have a long wavelength, you can think of it as a little baby. That's a baby. And if you put a baby in, okay, maybe like a little chihuahua. I probably shouldn't equate babies and chihuahuas, but so that's a little chihuahua. The chihuahua doesn't have enough energy to push the electron, so nothing happens. So that's your red light. If you put, that's your red light. But if you were to put like a toddler, they have enough force to push this box, so the electron is going to move, but it's going to move fairly slowly. Yeah. But if you were to then put a high energy photon, let's say this is an elephant, then the box is going to move, and not only is it going to move, it's going to move really, really fast because the energy that you supply into it is faster, is much bigger. Yeah. UV light, X-rays, and things like that. Yeah, but this one here is a shorter, a really, really very short wavelength. So the energy of your photon is a spectrum of how short the wavelength is, essentially. Yeah. Yeah.
So to restate basically that the big change in thought is doesn't matter how many photons is hitting the substance, it's based off of the wavelength of each individual photon.
Yep.
Because if the individual photon is of a short enough wavelength, then it has the ability to eject electrons.
Yeah. And so if we follow the same analogy, is that no matter how many chihuahuas that you put into it, it still won't be able to push any boxes because it's too low in energy. Analogy always breaks down. Analogy always breaks down at some point, so that's why they're called analogies.
Could you say intensity is analogous to amplitude, or should I not make that association?
They are the same thing.
Okay.
Intensity, you can think of intensities of the number of chihuahuas. Essentially, if you have your electron, your metal has a lot of electrons. That is, if you put one photon, what happens is that one photon is always going to interact with only one electron. Hence, it's a particle-like in nature that only one photons and one electron interact with one another. So if you
had a bunch of chihuahuas, they're only taking turns.
Yeah, they take turns, and essentially they don't push all one things at the same time. But so essentially, if you have two photons, so this is, if you only have one photon, then you're going to emit only one electrons at a time. Right, so one photon, only one electron moves. If you have two photons, then now you have two electrons that moves. And of course, if you have 3, 4, and so on, then you have more. So essentially, the intensity, so the intensity is here, is equal to the number of particles of light. And the same thing with this particular elephant. The more intensity that you have, the more elephants essentially in the room that pushes. Of light, of photon, yes. So same thing. That is. Sure. So. Sure. So if your y-axis is the kinetic energy of the photon, and the x-axis is the wavelength, how would this graph look like? Actually, let's do this. Let's make it easier first. Energy of photon. So, which is going to be E equals to hc over lambda, which is hc. Sorry, yes, kinetic energy of ejected electron. Sorry, I'm switching my x and y axis here, but let's start with this one first. So, if I shine a low energy photon, say a microwave, onto the surface of the metal, what is the energy of the ejected what is the energy of the ejected electrons? Lower. But remember, specifically 0, because nothing's going to happen. No electron is going to be ejected at all. So in fact, initially it's going to be 0, because the electrons are not ejected, their energy is 0. They don't move, so the velocity is 0, the speed is 0, kinetic energy is 0. But only until you hit a particular threshold, and this particular threshold of energy is called the work function, then the kinetic energy is going to gets bigger and bigger and bigger, and specifically they're going to be linearly related from one to the other. Yeah? It's the same thing that we've been saying before, except now it's placed into a graph.
I thought it was so that like that energy at 0. If it was dark light, you think the threshold is not going to increase, and that will electrons are ever going to get
If your energy, if the energy of your photon is exactly the energy of your work function, then the kinetic energy of your electron is going to be 0, right? So if this is 5, this is 5, 5 equals to 5 plus x. So x equals to 0. So essentially, it's when it's just on the threshold, nothing's going to happen. You need to have it just a little bit over the threshold for you to see something. It's like, I need enough force to break this pen. Yeah. No. Well, this is an entire spectrum, right?
Okay.
Right. I'm just trying to show that red light, low energy, UV light, higher energy, and so on. Yeah.
The energy of the photon is the energy of the work function. Kinetic energy is going to be 0, and no electrons will be ejected.
Yeah. So yeah, it's the energy of your photon is equals to the work function plus the kinetic energy of electron. So if this is 5 equals to 5 plus x, x must be equals to 0. Something like that. Yeah. Same.
You have to really do it earlier when we talked about ionization. It would be enough to get it to ionization, but then have no energy left over to impart any kinetic energy.
Yeah. So it's you can think of it as just outside, and it just came back in almost immediately, because it doesn't have, there's not enough things to break. Yeah. It doesn't have. It's just exactly right. Actually, most of the time this portion here is much more complicated than that, but we'll just, whenever you're in the brink of something, any little changes is going to make a huge difference, whether it falls or not. So we're going to assume for now that at the threshold nothing happens. So that's one. So how about if I were to ask you to draw, well, why not? So why don't you try to draw this on your own as well? So what if we have number of photon hitting the metal. So essentially you have more particles of light hitting the metal, and I want you to show what happens to this is actually going to be this is why you don't come up with questions on the spot. Yeah, photons are a thing, and no, why not? So we'll do the same thing, energy of the photon, which is hb. So what would happen? Can you even draw this thing? Oh, sorry. You have the y. So number of electron ejected. And let's do this for 3 different colors. So let's do this for different wavelengths. So let's just say the work function, I'm going to use the electron volt unit. So the work function is 1 electron volt. It's just a unit of energy. And you have 3 different wavelengths. You have wavelength number 1 with an energy of 0.5 electron volts. You have wavelength 2 with an energy of 1.5 electron volts, and then you have wavelength 3 with an energy of 3 electron volts. What would it look like of the number of photon being hit on the surface of the metal versus the number of electrons ejected? Right. So for one, let's do wavelength 1 here as the lower energy, so I'm going to use the red color. So I know that the energy of my photon is less than the work function, so I don't have enough energy to detach the electrons. I don't have enough energy to break the thing, so it really doesn't matter how many photons of light that I put in, the number of rejected electrons is going to be 0. Right? So this is wavelength 1. If I were to use, say, a wavelength 2, which is slightly higher in energy, and it's beyond the work function, so I know the number of ejected electron is going to be equal to the number of the photon that hits the surface of the metal, because one photon plucks off 1 electron at a time. Whereas the last one here, I'm going to use the purple color just to kind of show that this is UV. It really doesn't matter that the purple ones are going to line up exactly the same as the blue one as well. So it's the same thing that we've been talking about, but now it's just in a graphical format, so the question becomes a little bit confusing. These kinds of questions takes a bit of time to think about it, so don't worry too much about it for now.
So when actually the 1.5 electron volt is going to be a smaller slope than the one
No, exactly the same, because 1 photon ejects 1 electron, 1-to-1 ratio. 1 photons, 1 electron, 2 and 2, 3 and 3. Because each of the particle have enough energy to detach 1. So if you put 3 light photons, it's going to detach 3 electrons. Same thing, 3 and 3. They just move faster, but the number of electrons comes out is exactly the same. So, but for now, we're going to do, at least you should understand this part. Right, so this one is common, I should say. Whereas this one is just a little bit just uncommon. I started with the uncommon one in the last because I couldn't think of anything else. So anyway, so these are the common ones, so something like this you should understand conceptually at the very least. It's like what it should look like. Simply says that there's a threshold. If you don't have if the energy of your photon is not enough to overcome this threshold, nothing happens. Whereas once it has enough threshold, then you see a bunch of stuff coming out. Yeah.
Enough threshold, we kind of think about it, what kind of weight cell right there, with 2 seconds to get going with this one.
Yep.
So that, whatever it takes, 1 or 2 seconds to pass the threshold right there, and then after that, then I can start increasing.
Yeah, if you put you and I both in a bazooka, you're going to move faster because you're lighter, whereas I'm heavy, so I'm just going to move like a turtle. It's something like that. It's the same thing. That's as close as a classical thing. But yeah. What I do want you to be able to do for now is just do the math, because it is kind of math-based. So I already asked that particular question, I already asked that particular one. Let's do this one. Let's do, this is the next question. So, what you want to know is the wavelength of the radiation. So what you want to know is the wavelength of the photon. What you know is going to be the work function of chromium metal. In this case, the work function is 4.37 electron volt. And you also know that the electron moves with a velocity of 15 times 10 to the power 3 meters per second. That might be a typo, but it's alright. The velocity of electron is 15,000 10 to the power 3 meters per second. And how do you solve for the problem? Okay. And the equation that you needed is on the previous page. For one, we know that this is a photoelectric effect, so the main important equation is that the energy of the photon is equal to the work function plus the kinetic energy of the ejected electron. Right. So I'll start from there. And some unit conversion thing is that 1 electron volt is going to be equal to 1.609 times 10 to the power of negative 19 joule. You can answer, give me your answer either in electron volt, it's perfectly fine. You can work your way with a problem with electron volt or using joule. And another useful conversion factor is that 1240 is equals to the energy of a photon in electron volt unit times the wavelength of the photon in nanometer. But if you don't want to use that, it's perfectly fine too. So this is what you want to know. This is what you want to calculate, the wavelength of the photon. And what you know is the work function as well as the velocity of the electron. Alright, so same as before, just kind of turn around, work on this particular question. And why don't we try to work on this particular page completely? So we have 3 problems here, so we'll do 3 to 4 problems. So why don't we try to work on this together? So Paul and Anthony. No, it's not Anthony. It is Anthony. Yes. So just kind of twist your chair. We'll work together, and in the meantime, I'll print out your stuff, that thing, and we'll go to that.